Now we're going to look at creating a confidence interval for sample means. So the state and plan, first of all, our name for our method or a test is a two-sample t-interval for mu. Now remember, you also need to check the large normal sample condition. So those are how things have changed from the tests that we were doing before, or the confidence intervals. So we're going to complete the state and plan steps for this example. We have a coffee machine that dispenses coffee into paper cups. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. Here are the amounts measured in a random sample of 20 cups. Construct and interpret a 95% confidence interval. So they want a 95% confidence interval for the true mean ounces of coffee dispensed. So our plan is to do a one sample t-interval for the mean. Is it random? They told us that it was random. It's given in the problem. 10%, 20 cups is less than 10% of all cups. And the nearly normal condition, I went ahead and did a histogram here. So I entered the data in a list and did a histogram like we learned how to do earlier in the year. And you can see it's roughly unimodal and symmetric. So the condition's met even though my sample size is less than 30. So you can probably recall we've been doing critical values for z for the normal distribution, and that we used inverse norm, which only uses the area to the left of the critical value for z. Now we have a similar function on calculators for the t distribution. So we're going to press second in distribution. It's in the same area, and in fact it's right under inverse norm. So you're going to scroll to this inverse t. When you are prompted for area, use the area to the left of t. And for degrees of freedom, you're going to use n minus 1. All right, so you'll see area and degrees of freedom. If you have an older calculator, what you'll see is something like inverse t with the parentheses. Just put left area, comma, df, and you have it there. All right, so critical values for t are calculated similarly to z. Basically, when we do a confidence interval, we're centered. All right, we're not on the left or the right, we're centered. So if we have 95% in here, we're going to divide the leftover 5% between the two. And so if I use that as my critical value, I'm just going to take that area and put in the degrees of freedom. So it's 1 minus the confidence level like before, divided by 2. But now I have this new thing called degrees of freedom because there's a different curve for every degree of freedom. So let's go ahead and calculate some critical values. We'll do a 90% one. So 1 minus 0.9 over 2. And my degrees of freedom is 35 minus 1. That works out to 0.05 and 34. And I get negative 1.691. I'll be using the positive, but because I know there's a positive on that side as well. And actually, we use them both to do the interval. All right, let's do the 80%. Inverse t of 1 minus 0.8 over 2. And then my degrees of freedom is 12 minus 1. So that's what I enter in the calculator. And I get negative 1.363. So our do for confidence intervals is very similar as what we've been doing for proportions. It's still your statistic plus or minus your critical value times your standard error for your statistic. For sample means, the statistic is a point estimate for the mean, and the critical value is now a t-value from the student's distribution. So we can rewrite it like this. And remember, you can use 1var stats on your table of data to calculate S of x, which would be basically right here where this sigma is. So the do part is now very similar to what we were doing before with proportions. On the formula chart, it's the same thing. They don't actually give you this piece down here. It's the statistic plus or minus your critical value times your standard error or standard deviation for the statistic. Now our critical value is coming from the t-distribution, so we can rewrite the entire formula to say it's your x bar from your sample times your critical t-value times your standard deviation for your standard error for your sample divided by the square root of the sample size. Now remember, you can get this S of x by using 1var stat. So you'll probably be entering the data in, and we will show that to you in an example shortly. Conclude is also the exact same, except, just make sure you're in context. So we're about making a prediction of having captured the parameter. We don't say this is the probability that the parameter is in somewhere because the parameter is fixed. It is not moving around. Okay? So let's go ahead and complete the do and conclude steps for this. I have my X bar. What I did is I entered all this data in a list in the table. So I put it in list 1, and then I ran one var stats on that list. I have my mean is 9.845. My standard error for my sample is 0.1986. Sample size is 20. My degrees of freedom, I went ahead and calculated that as 19. I can calculate the standard error for the mean. Notice how I have X bar here instead of just X. And I get 0.044. All right. I also need a critical value. And I'm going to do inverse T. I want a 95% confidence interval. So that's going to end up being 0.05 up here, 0.025 with 19. And if I do inverse T on my calculator, that's the number I get. So my confidence interval is my point estimate plus or minus my critical value times my standard error for the mean, all right? Which gives me this interval right here. We are 95% confident that the machine dispenses an average of between 9.75 and 9.94 fluid ounces per cup. You could argue because this interval doesn't have 10 ounces in it, they're shorting them a little bit. All right,